Okay, we started recording for today, so could I have everyone's attention, please? Today we are going to go over electrostatics specifically. We are going to find the electric fields due to multiple charges, and charge distributions. Last time in class we found the electric fields due to a single charge. Now we're going to extend that to charge distributions. We actually got started on this at the end of class last time, but we didn't get a chance to finish. So we're just going to have to start again from the concept. Before we do that, homework questions. So let me open the homework here. And I'm glad we have the homework questions because this class is a lot about problem solving. And so I'm fine with spending time in class like going over homework problems, because you'll see that compared to another class, there's actually less material thrown at you, but there's a lot of problems that you have to do with it. So let's go to homework 3. All right. Ask away. Number 4, 4A. Okay. A single surface. Huh. Okay. So do you want help in setting up the problem, or did you have a specific question about it? Okay. Right. This stuff was on the last module, so. All right, so this question is asking you to find the total flux on the surface of a sphere. All right, we talked about this earlier in class today, or earlier at office hours today. So Jeremy, there may be other people in the class maybe thinking along the same lines what you were thinking. So maybe you can explain to them, your initial approach and what we ultimately decided on. Yeah. Yeah, sure. Feel free to talk about it. Yeah, so Jeremy was initially thinking of splitting the sphere up into multiple parts and doing multiple surface integrals. One of the reasons for that, and I realized it's actually, I can see how this happened. Like if, in the previous problem, when you're doing surface integrals, and every one that we've done in class, we've had to do multiple surface integrals, right? To find the flux. But the nice thing, because all the surfaces have discontinuities in them. Yeah, that's a succinct summary, right? So all these all these planes in the square, they have different equations associated with them. This plane up here was z equals 1. The plane at the bottom is z equals 0. The plane here is y equals 1, and here is y equals 0, right? But the nice thing about the sphere is that everywhere on the sphere, r is equal to 1. So it's actually only a single surface that you have to integrate here. What's that? R equal to A, yeah. Did I say something else? Oh, okay, sorry about that. R is equal to A, yeah. So, this is an example of where to find the total flux, you only have to do a single integral. A double integral, yeah, I'm sorry, a double integral, but you only have to do one of them, right? And so what you find in part A, part A here, you have this a double integral that you need to do. In part B, you try to find the same flux using the volume integral of the divergence. So this is one of those situations where surface integral actually ends up being less work than the volume integral. In this problem, in the previous problem, you likely saw that the volume integral was much, much, much less work than the surface integrals. So this is what I'm talking about. Like after you do some problems like this, you'll get a sense for which of the two methods requires the least amount of work. And as an engineer, you'll do that. Yes, Justine. Yes. Yeah, that's an excellent point. Justine brought up the point is that when we're doing these, when we're doing not just the divergence theorem, but when we're doing Stokes' theorem, we have to sometimes calculating the divergence del dot E or the curl del cross E. It can start to get pretty hairy because you have to, if you're in spherical or cylindrical coordinates, finding the curl and divergence of a field can get, you have to use the formulas on the table, and they can become kind of complex. So I agree with you. In some cases, the line or the surface integrals may end up being less work. So that's just something you have to get a feel for and sort of decide. I think in the exam, I will probably give you some problems where you're going to use both methods, and you should arrive at the same answer. So it's a way of self-checking, So that that's a good question. Are we going to have time to finish them? Let me get a sense for how long did it take you all to do these problems? A few hours? Okay. A few hours for one problem or the homework? For the homework? Okay. 3 to 4? Okay. About 5? Okay. Yeah, that's fine. I mean, the more time you spend on these homeworks, the more you learn from it, really. It's great. And, like you should you should expect to spend, since this is a 4 credit hour class, you should expect to spend at least 12 hours a week out of class. So, I mean, if you're spending 6 hours on homework, I think you're doing fine. If you're spending 10, 12 hours, that's also fine. You're probably more in line. If you guys want more homework problems to more like practice, I can assign more problems. There's a lot of problems in the book on it. These are all really, I'm telling you, it's just to prepare for the exams. The exams really count for most of your grade. Every problem that you do during your homework, you're just preparing for your exam. Some of them are adapted from the book. I've taken some of these problems from different books. So, and some of them are probably from the book that, the Ulubi book. Right, so I take them from a combination of sources depending on like what we cover in class and what I want you all to learn. Yep. Yeah, for that, what I could do is I could suggest some problems. I could suggest some problems from the book, and those problems actually have answers in the back of the book. The exam will be on Wednesday. Yes. Not next week Wednesday, but the week after that. So we have this week we're going to cover material. Next week, on Monday, we're going to cover some material. So we have 3 lectures of material that we're going to cover. And then Wednesday, I'm going to collect the final homeworks. We're going to review them. We'll probably go over the problems in class. And then I will actually be gone the following week. I'll still have access to emails so I can reply to emails, but the exam will be Wednesday that week, the week that I'm gone. Yeah, we could have the exam Monday also if you'd like. But I figured students usually like to have the exam as late as possible. So that's why I'm saying Wednesday. You'll have Monday off to study, and then off. Monday can be your study day, and then Wednesday you'll have the exam. Right? And I suggest studying together. You guys could even do this. If everyone comes to class that Monday, you all could just have a big study session together. This room will be open, because we're expected to have class during this time. So let's do that. Plan on it. 2 weeks from today, everyone come in here 2 days before exam, help each other out, learn from each other. Yeah. Okay. Sure. Fair enough. Yep. Come on up. Did you want to draw on the word thing or just in OneNote? There we go.
Okay, so start with, learn to draw again. Okay. B is equal to that sine plus. Okay, that's where we start. We want to go to Cartesian, so x of y, since we're in 2 dimensions. And the equation for that is AR. No, I don't believe there is. Yes, and that's on my paper. Okay. Thank you. I would be very confused later when I got there. Yeah, okay. AR cosine. I move this whole thing. Yeah. Oh, finger. Okay, awesome. Okay, A phi at
Isaac's doing right now is he's converting a field that's given in cylindrical coordinates, and he's or cylindrical or spherical?
cylindrical. This is one of the flat problems.
Because MATLAB can only plot in Cartesian coordinates. So in order to do this, Isaac, do you mind if I just borrow the screen for just a second? I want to remind everyone where this is coming from. If you want to do Wikipedia is fine. It turns out it's pretty accurate. So, because Jeremy, you were asking about this earlier today too. If you want to do a coordinate transform, look here in the notes. It's slide 61. All right. So we want to convert cylindrical to Cartesian. All right. So Isaac is using these formulas right now. All right. It converts the vector components in cylindrical coordinates to vector components in Cartesian. All right. So whatever coordinate transform you're trying to do, this is the chart to look at. In addition to this, you're also going to have to use this part of the chart too, because when you're given when you are given a field in terms of r and phi, you have to convert those variables r and phi into x, y, and z. So you're going to be using this section here to convert all your r, phi, and z variables into x, y, and z.
Okay, so this ends up turning into a long mess. Yeah. Oh, let me write it out because I know that if you talk it at me, I'm gonna go, I have no idea.
So I think should we write out the whole thing? Because I mean I don't want to just put the solution on there.
Oh yes. I mean this is just I have the equation on the top that we're converting, and then that's the method I was going to write the equation out that it generates.
Okay.
I just want to make sure that I'm not off base. So that's R. Okay, so R cosine phi multiplied by cosine phi, because that's AR cosine, so that's squared, minus sine phi multiplied by sine phi, so that's squared.
Pretty much what you were getting earlier today, right?
X hat plus sine phi plus phi y hat. Okay, so then for simplification, x is equal to r cosine. No.
Oh, that seems really temperamental. Sometimes it just stops working.
There we go. I'll just scribble like it's a pen. Cosine phi. Well, and then it stopped again. There we go. Okay. So, using this, phi equals 10 to the negative 1 y over x, which is the one that's actually a mess. And also, I used another identity. Where did I write it? I didn't write it. Okay, so I also used some other trig identities, but this top part is in fact correct. Like that's what you do, and then start plugging in to remove all of the phi's.
You do, but as Jeremy and I were discussing today, there's, everywhere you have a cosine phi, if you actually put in cosine of inverse tangent of y over x, that can get kind of complicated. Instead, you can use the relations that you've just shown on the left, x equals cosine phi.
Yeah.
Wherever you have a cosine phi, just replace it with x.
Well, it's r cosine. It's r cosine phi.
Yeah, so you'll be x over r.
Oh, that's a lot simpler. Okay.
I just told you I knew the problem.
Yeah. Well,
I know exactly what you were talking about because we were thinking the same thing earlier today.
Okay. Okay. So you can also use that cosine. Oh, thank you. And phi is also equal to x over r, so you can. Okay, you can use that to convert as well.
Yeah. That makes things a lot cleaner.
Okay. Yeah, and then you can use the r to only have it. You can convert r into. Okay, that'll make my equation a lot easier. Right. Thank you.
Good point brought up by Isaac. Thank you. Yeah, he just saved you all an hour on your work. Yes. Uh-huh. Yes. And that's exactly what Isaac had done. It didn't complain at you that you were trying to do y over x at x equals 0? Oh, okay. Well, did you when you assigned your values of x, when you're plotting, you have to assign a vector of x and a vector of y values, right? Did your vector of x values include 0? It should include 0. Yeah, it should include 0. So some MATLAB sometimes would complain that you say dividing by 0, and sometimes it'll do the calculation and it'll just say NaN, which means not a number, or it'll give INF infinite, and it just won't plot it, which is fine. But if you're seeing right, right, yeah, yeah, Jeremy. Warning that you have a division by, huh? That I don't know. Okay. I don't know if we'll be able to figure that out right now. Okay, let's do other questions on the homework. One thing I would like to clarify. In question 5, you are asked to calculate the circulation of a 2D vector field, and this is in cylindrical coordinates. Okay. When you do the line integrals, when you do the surface integral, do them in cylindrical coordinates. Don't convert this to Cartesian and then do the calculations in Cartesian. It will be miserable. The conversion to Cartesian is just for part A, just so you can plot it in MATLAB. I would like you to be able to visualize the field. And actually, Justine actually has the plot of what the field look like, so you can go bug her after class if you want some help on that. I just volunteered you, Justine, sorry. For part B. Mm-hmm. Mm-hmm. This is one of the lines? Bottom. Okay, so here. 1 to 2. Phi equals 0. Correct. Correct. Yeah, so the question is, what is DL? Yeah, and for this kind of problem, you can just look at it by inspection. And you can just say that, you can just see that, oh, you're going in the R hat direction. So it's just R hat. It's R hat dr. I'm sorry? Yes. R hat dr is what it is. So let me show you let me just remind you all what the in Cartesian coordinates. What is DL in Cartesian coordinates? Dx, dy, dz. Right? In cylindrical coordinates. Cylindrical. dl equals, all right, so what's the first component? dr, right? Next one, r d phi, and dz. And remember, you know, the other form of this is r hat dr plus, oh, jeez. Today's one of those days, it's not liking it. Okay. I figured out a way to fix this sometimes. To restart the OneNote. Sometimes it works. Today it's not. It's actually just a crappy pen. So I'm in a couple weeks I'm getting the new Surface Book, and the pen on that is awesome. So that's part of the reason why. Okay. So if this doesn't work, then I will just draw on the board. Yeah, looks like I'm drawing on the board today. Okay. And cylindrical coordinates, dr, r d phi, and dz. How about spherical? All the time. Now, the question was along this hemisphere. These are the general equations for DL. When you're doing line integrals, a key step is that you have to then take this general equation for DL and plug it into the actual line that you have. Right? So we are in the cylindrical coordinates regime. This is our general equation for DL. So DL is going to be different depending on which of these four lines you're on. So this is going from 1 to 2. Right? So this is the first line that we're integrating. Right? So the first line, the equation for the line is just phi equals 0. Right? Everywhere along this line, phi equals 0. Now, you may have more complex equations for lines. Like if you were in a Cartesian coordinate system and we're integrating along those parabolas, y equals x squared. You have to put in that equation, y equals x squared, and then solve for DL along that line. Right? So what we're doing here is a simple example. This defines the line. Define the line first, and then calculate your DL. So now your DL is equal to dr times r d phi dz. All right. So your r value is going to go from 1 to 2 here. Right? So your r is not a constant. It's not a constant. It's going from 1 to 2 on this line. So you're going to have a dr here. Your phi is equal to 0. Right? If your phi is equal to 0, what's d phi? 0. Just goes away. This is a two-dimensional problem. So what's the value of z? 0. What's dz? 0. So this particular line, this is what dl is equal to. Let's try the next line. What's the equation for this line? It's a quarter circle. Along the second one, r is equal to 2. That's the equation for the line. dl equals dr, r d phi, dc. Right? So your r is a constant. What is dr? R is equal to 0. All right, what is r d phi? Why is it not 0? Exactly. So phi is varying from 0 to pi over 2 in this case. Right? It's a variable. So d phi is not going to be equal to 0 along this line. And the r value is equal to 2. So it's just 2 times d phi. How about dz? Let me show you one more example in Cartesian coordinates. Suppose we're doing a line integral along here. Y equals x squared. We did this example in class too, but let's just touch on this again. Let me just erase this. Yeah, so let's say I was just asking you to calculate a line integral along the vertical. Well, the equation for the line is y equals x squared. So what is our dl going to be equal to? dl is equal to dx. Y. Always. Always. Your Cartesian coordinates always equal to this. That's your starting point. Now you take the fact that you're along the line y equals x squared and you substitute those values into this equation. So how are we going to do this? Okay, so we want to differentiate this equation. Sometimes differentiating the equation can help us. What happens if we take the derivative of both sides? dy equals 2x dx. Don't forget the dx. Because this is what helps you. So what we do here is, remember, we're going to be doing a line integral. So we want to put everything in terms of one variable. Why? Because a line integral is like this, right? A line integral is just you're integrating over a single variable, a single parameter. So you want to put your dl in terms of one variable. So if I'm going to evaluate the line integral between here and here, what's going to be my variable of integration? We're integrating from x equals 0 to 1. So if we're going to integrate, if we're going to do an integration with respect to x, let's put everything in terms of x. Right? dy is equal to 2x dx. So we're going to be doing an integral with respect to x. So let's keep that dx in there. What's our dy going to be? 2x dx. dz, what is dz going to be? 0, because we're in a two-dimensional problem. Right? So when then your next part of the problem is, let's say you have some kind of vector field. You do the integral of f dot dl. So this will become the integral from x equals 0 to x equals 1 of whatever your vector field happens to be, dotted with to simplify this into an equation that just involves x. So these finite integrals, if you follow this approach, if you always start with these first, and then you figure out what the equation for the line is that you're integrating across, it's very methodical and it works every single time. Hopefully. Last question. Okay. Yeah. So the last question has to do, has to do with line integrals as well. You have like these 3 different lines here. The key is to find equations for each of those 3 lines. In a Cartesian coordinate system, you'll be able to figure out equations for those 3 lines. You got it. What's that? So, I don't want to give away too much more of the rest of the problem. I want everyone to have a chance to try it on their own. But well, you can figure out what your DL is just by following this procedure. You're in the Cartesian coordinate system, so your DL is dx, dy, dz. In each one of those 3 different lines, your DL might have slightly different values. Because you're going to plug in the equation for the line into the DL thing. Got it? Yes, you're going to be integrating from 1 to 0. Y equals 1 to y equals 0. Okay. When you do Stokes' theorem, you have to actually integrate the curl over a triangular area, which is a type of problem that we did in the previous homework. So it ties in a lot of the concepts. All right. Any other questions? The homework. Good. So glad to see that everyone's trying this and making progress on it. All right. I'm going to close some of these things so I can get my pen working, and then we'll go on to cover some new material. It's probably the MATLAB. All right. I'll just close some of these. All right, now let's see if this thing adds it over. Ah, there we go. Just wasn't happy because there's too many other programs open. Okay. All right, so we're going to cover some more electrostatics today. Great fun, right? So what are we doing today? We are essentially going to be talking about this first rule of electrostatics. Del dot D is equal to rho V. And remember, Maxwell equation, if we translate that to plain English, what that means is that electric field lines point away from positive charge and they point towards negative charge. That's the English translation of Maxwell equation number 1. All right, so what we're doing today is we are looking at different charge densities. There's volumetric charge densities, surface charge densities, and line charge densities. And we can even think about individual charges, like a single point charge, for example. And we're going to calculate the electric fields as a result of those charges. Last time in class, what we did was we did an example of Coulomb's law. Coulomb's law describes the electric field coming from a single point source. And so assume that you have a point source in the middle and you're at some kind of observation point. And there's a vector, r, that points from the origin, where the charge is, to the observation point. And that r vector has some kind of length associated with it. The Coulomb's law tells us that the electric field at that point is equal to Q divided by 4 pi epsilon r squared. Now, this r is the magnitude of this vector. And then r hat is the unit vector of that vector. And if we placed some kind of charge here, that the electric field would create a force on that charged particle. Right, so we did this example last time. What's the electric field 2 nanometers away from a proton? If we had another proton at that location, what's the repulsive force? We figured that out. And we generalized Coulomb's law by saying, well, what if the charge is not located at the origin? What if it's somewhere else? And we came up with these equations here, where instead of this just a single r vector, you have r2 minus r1. R2 is the coordinates of point P, that's the observation point, and r1 are the coordinates of where the charge is located. You have some arbitrary point P in a three-dimensional space, and you have some arbitrary charge located, another charge located at an arbitrary point in space, that's Q. So R2 is the coordinates of P, R1 is the coordinates of Q. R2 minus R1 is a vector that points from Q to P. That's the key thing here. R2 minus R1 is a vector that points from Q to P. All right, so you have R2 minus R1 divided by R2 minus R1 magnitude cubed times Q over 4 pi epsilon. So that's how you find the electric field from two arbitrary points. We did this example, I believe, last time. We didn't get to this example, so this is going to be as homework. This is, does anyone want to do this in class, or do we want to just have it as homework? Okay, there's this, so that's a no vote. Others? Any yes votes? Okay, well, let's leave it for now. If you have trouble on the homework problem, which I don't anticipate, but if you do, if anything's confusing, please let me know. We'll go over it together in class. So the example here is that you have 4 points on the corners of a square with edge length 1. At each of the points, there's a charge starting from the top left. You have these amount of charges, 1, 2, 3, and 4 in coulombs. What's the field in the middle? So, if we were to draw that out, it would look something like this. Imagine you have 4. Oh, you gotta be kidding me. Imagine you have 4 points around the corners of a square. And this has 1, 2, 3, and 4 coulombs of charge, and you're asked to find the electric field at the point in the middle of the square. You have to do 4 different problems. You have to find the electric field due to charge number 1, then you have to find the electric field due to charge number 2, the electric field due to this charge, and the electric field due to this charge. And you add them all together. That's superposition. All right, today we're going to do electric fields due to a charge distribution. We did get started on this problem last time. We will continue it. And if I have problems with my pen, I'll just do this problem on the board. So this type of problem, the one we just did, is due to discrete charges. individual charges in space. Now, in real life, it's kind of hard to just have point charges in space, or usually we end up working with things that are more like charge distributions. For example, the most common type of electrostatic element that we come across as electrical engineers is a capacitor, right? What type of charge distribution is a capacitor? Yeah, well, in terms of like what were the terms that we're using in this class, there's three types of charge distributions that we talked about. Exactly, a surface charge. It's a surface charge. So these are the different types of charge distributions. One is a linear charge distribution where you have like a thin line or a rod, and the charge density is given in terms of coulombs per meter. In a capacitor is like a sheet charge. So there's a surface charge density, and there's if you imagine like the classic model of the capacitor where you have positive charges on the upper plate, negative charges on the lower plate. Those are sheets of charge. The charge density is given in coulombs per meter squared. And then in other situations, you might have volumetric charge density, coulombs per meter cubed. If I say I have a cube, I have this a charged dielectric material, and that dielectric material has this many charges per square meter. That's a volumetric charge density. So depending on which one you have, there's three different equations you'll use, but the basic idea to find the electric field due to a charge distribution is that you have to add up the components, add up the contributions of each charge that's found. Just like we did here, if this is our observation point P, we find the electric field due to charge 1, we find the electric field due to charge 2, electric field due to charge 3, and electric field due to charge 4. Just like we did in this example problem. We're not going to do this problem, but it's worth it to kind of see. So if this is charge 1, we'll call this Q1, Q2, Q3, and then Q4. What's the electric field going to be at this point due to Q1? Which direction is it going to point? Downwards and to the right. Yeah. If we were to draw a straight line, like this to the observation point, the electric field will point in this direction. The electric field from Q2 will point in this direction. Electric field from Q3 will point in this direction, and so on. And Q4 will point in that last direction there. I'm sorry? Opposite way? Say it again. Yes. Yeah. It basically, if I were to draw a line from Q4 towards the charge, and I just kept that line going, that's the direction the electric field would point. All right. But now we're doing charge distributions. When we do charge distributions, we don't just add up the effective discrete charges. We actually integrate. Because remember, when you're integrating means adding up. So we can integrate over a volume. So we're, in essence, we are adding up all the charge contributions from all the charges in a volume. If it's a surface charge density, we can do a double integral, which adds up all the contributions from all the charges on the surface, or a line integral, which is what we're going to do an example of, where we're adding up all the contributions along a line or one dimension. So what does a line distribution look like? Looks something like this. Find the electric field around an infinitely long wire. So imagine that we're going to imagine this in the, we can do it in a Cartesian coordinate system. This is Z, this is R, but it can also be like X and Y. So if we draw it in the XY system, that's the coordinate system we'll use today. And this line, this wire, has a uniform charge density rho L given in coulombs per meter. And the question is, determine the electric field intensity of an infinitely long straight line of charge, with uniform density, at some point r away from it. Right? So imagine that we have some kind of observation point. It's right here, and the distance to the wire is r. The question is, what is the electric field at that point? So how would we go about attacking this problem? All right, what's the first step in this problem? What's that? Okay, yeah, we can set up the equation. Let me grab my notes here. There's a few tricky aspects to this problem, but we'll start from the basics first. So we have this infinitely long wire. And this is, let's call this distance A. We're at some distance away from this. And we can think about this thing going infinitely long here. Oh. Okay. All right. So we want to find the total electric field. This is the equation that we'd want to use. The line charge density, 1 over 4 pi epsilon integral of AR hat rho L over R squared dl. So let's write that down. E equals 1 over 4 pi epsilon integral of AR at rho L over R squared dl. All right, just like before, we want to break this problem down into the different parts that the equation is telling us. And in doing that, we'll hopefully build some intuition on the problem too. What is dl, first of all? In this case, what is dl? dz. Why is it dz? Yes, exactly. So what we're doing here is imagine a bunch of charges like this. It's just a line of charge. So the key thing is that it's given to us in units of coulombs per meter. Oh man, this thing's really being uncooperative today. If it continues to do this, maybe I'll just use the board. What do you think? Should I use the board? I don't have an option. Maybe when battery's out. No, I taught it 4 years ago. I had to restudy everything just like you guys. Well, we are we do have some, we can choose which courses we'd like to teach, but ultimately, like, sometimes we have to, if there's a change in schedule or something, then, we do whatever the department, wherever the department needs are. I've never taught linear. That's a difficult class, I hear. Well, are you guys all taking linear this semester? I think Professor. Thank you. I appreciate that. That's what I try to do. Well, thank you. We're all getting A's. Sometimes the battery goes out. All right, a little bit better. All right. So the electric field is equal to, so imagine just a bunch of positive charges here like this. And just qualitatively speaking, what is the electric field going to look like here? So imagine adding up all the contributions of all the charges from here, right? Let's start with this charge up here. The contribution from this charge up here, what's going to be the electric field direction from that charge? Yeah, it's going to go something like this. So this is going to be, let's call this E1. Okay? So that is the contribution from this charge here, 1. And let's call this one E2. The charge contribution from E2 is going to point in this direction. So this is one of the key things about symmetry in this problem. What happens when I add up E1 and E2? You don't get zeros. What's that? You have a vector that points straight out. Exactly. Why is that, Jeremy? The z components cancel. Exactly. All right, so like E2, the two components of E2 are, this is the x and this is the y. Or, I'm sorry, this is the x and this is the z. This is z coordinate. What are the coordinates of E1? X and negative z, right? They're pointing in, the z components are pointing in opposite directions. When we add those up, we're going to end up with a vector that just looks like this. So, based on that, what do you expect the electric field to look like at A? What's going to be the direction of the electric field? It's going to be just in the x direction. Question, would anyone like me to go over that again? Why the electric field is just going to be in the x direction? You could do that. Yeah. Noah brings up a good point. We're not going to be doing that in the problem today as we're doing it, but Noah brings up the point where that instead of integrating from negative infinity to infinity, we could just integrate from here to here and then double the x component, right? And we know that the z components are going to cancel. So yeah, you could do that. What do you mean by double the x component? A good question. I'm glad you brought that up. I guess I skipped over that pretty quick. So let's say this was E1. Okay, so this was charge 1, this was charge 2, this is E1, and then this is E2. All right, so if we're thinking about like what is E1 plus E2? This is the x component of E2, and this is the z component. And for E1, this is the x component, and this is the z component. The z components cancel out, but when you add up E1 and E2, you get twice the x component of E1 and E2. I'm sorry? In this problem, this is the x direction, and then this is the z direction. So the y is out like this. That's correct. DL is going in the z direction because we are integrating from here to here. We're integrating up the line of charge because we're adding up the contributions along that line of charge. Right. So we've established we know that there's only going to be an x component of this field. So we know that symmetry basically. So let's continue on and do 1 over 4 pi epsilon. All right, we know we're going to be integrating from z is equal. What's going to be our limits of integration? Infinitely long line. Exactly. Negative infinity to infinity. So we figured out what our dl is. It's dz. Once we figured out what dz was, then we have to figure out the limits of integration. And we just figured out that, of course, it's an infinite line. So we're going to go from z equals negative infinity to infinity. Now, next step. What is AR hat? Now, this is where the vector stuff starts to come into play. Not quite. Let's imagine we're at some point A, and remember we're integrating from z equals negative infinity to infinity, right? So we're gonna do everything in terms of a coordinate z. You remember about these line integrals? We were doing these line integrals, and we said, well, if you're integrating over a single variable, you should put everything in terms of that variable, right? So everything here, everything that you see here should be put in terms of z somehow. All right, so what do we have here? AR. AR is the unit vector that's pointing from the charge to the point, the observation point. So let's say we are at some point z here. Okay? All right, we're at some point z. And this is our observation point. So just like before, we want to find the electric field contribution from that charge at that point. I'm going to zoom in here for a second. So the electric field will obviously point in this direction. This is R. This is that vector R that points from where the charge is to the observation point. Now they're asking us to find AR. The formula is asking us to find AR. So we need to find let me write this down. I'll write it down up here. AR is equal to R divided by the magnitude of R. Right? We're just finding the unit vector in that direction. So R, remember, is a vector. R divided by the magnitude of R. All right, so R in Cartesian coordinates, what are we looking at here? So this is the vector R. I highlight it in red. This is R. What are the two components of R? So we're going to go down and across. All right, so we're going to go down. How much we're going to go down? Z. So there's negative Z. Make that a little bit larger. So we're going to go down negative Z, and we're going to go across how much? A. So R, let me write this. R is equal to negative Z times Z hat plus A times, let's call this R hat. Okay, X and R are kind of interchangeable here. Okay, we're in cylindrical coordinates. We can put things in terms of X and Y, or we could put things in terms of R. Right, because there's cylindrical symmetry around here. So I'm just going to put it in terms of R hat. All right, what's the magnitude of R? Right, square root of Z squared plus A squared. Great, perfect. Okay, so this AR hat is equal to R divided by the magnitude of R. So we can put negative Z times Z hat plus A times R hat. This is all divided by the square root of Z squared plus A squared. And then we also have rho L over R squared. Now R squared is actually, I should say, the magnitude of R squared. So what's the magnitude? So what is the magnitude of R squared? Yeah, Z squared. Oops. Z squared plus A squared. Perfect. All right, so we have the square root of Z squared plus A squared multiplied by Z squared plus A squared. It should be magnitude of R squared, yeah. So just a little bit of detail here. In these equations, wherever you see something in bold, bold means it's a vector quantity. If you see something that's not in bold, that means it is a scalar quantity. That means it's the magnitude of the vector. Yes. AR is the unit vector. So let's define things again. This is R, okay? R is a vector that points from some point where the charge is to the observation point. That's R. AR is the unit vector in the same direction. The unit vector is R divided by the magnitude of R. All right, so next step here, there's a couple things here. First of all, rho L. Rho L is a constant. So if it's a constant, we can just take that out of the integral, or move it out. So we move it out here. Rho L over 4 pi epsilon. All right. And let's keep our integral. Z equals negative infinity to infinity. Oh, absolutely. Yeah, I could say rho L is a function of Z, and you'd have to keep it in there. But in this particular problem, it's a constant. Now the denominator here, Z squared plus A squared. This is Z squared plus A squared to the half. This is Z squared plus A squared to the 1. So when you multiply these together, you get Z squared plus A squared to the power of 3 halves. All right, now the top one. which of these two terms can we just cross off due to our knowledge of symmetry that we talked about? The z hat term, right? We established that this vector, we know from symmetry, from our own intuition, that this vector field is not going to have a z component, it's just going to have an x component because of that symmetry. So we could go ahead and do the math for all this stuff, including z, but why do that when we know that the z's are going to cancel out? They should cancel out. So if you don't believe me, I think you can go ahead and do the math, and you'll actually see that those z terms will cancel out. But as an engineer, we often, like, if we know some things will cancel out, get rid of it. Make the math a little bit easier. We just got rid of that term entirely. Okay, let me explain that a little bit more. This is going to be integrating a force component in the z hat direction. This is going to be integrating a force component in the r hat direction. And again, like I said, if we actually did the integral of the z hat force component, we'd find that it adds up to 0. But we're not going to bother with that right now. Okay. We forgot to put dz in here. dz. All right. Next step. So that was a critical step there. All right. So now rho L over 4 pi epsilon. Now the next hurdle that we come across is, by the way, this a is a constant, so the a can be moved out here, rho L times a. Integral of z to negative infinity to infinity. Everyone with me so far? Feel free to stop me if there's any point of confusion we want to go over. So I'll make sure we know that this is, we know from symmetry that the field will have no z component. What's that? No, the z squared, no, this, just the z hat term, we're throwing that one out. Again, we don't have to, like, you can actually do the math, it'll cancel out on its own. Rho L is a constant, so that's why we can move that out. And A is also a constant, so we can move that out. And in fact, we can even move the r hat term out because it's not a function of z. Anything that's not a function of z, we can move out. So we're left with z squared plus a squared to the power of 3/2. All right, now who remembers how to solve this fun integral? Nope. But the problem is you don't have a du. So, since this is not a math class, I gave you that handy table of integrals. We're not going to bother coming up with the trick to integrate that. We'll just use the good old table. So if you look up, what are we looking at? Z squared plus a squared to the negative 3/2. All right, this is given in everything in terms of x. So let's see where we can find it here. There we go. X squared plus A squared to the power of 3/2. It's because it has a closed form solution, interestingly enough. You remembered it almost? Rho L over 4 pi epsilon A times R hat. So the solution of this is going to be 1 over A squared, Z squared plus A squared to the 1/2. Yeah. And this is over 1. And this is evaluated from Z equals negative infinity to infinity. Now, some of you may or may not remember doing integrals in terms of infinity. The mathematically rigorous way to do this would be to write limits everywhere, limit as this goes to infinity, limit as this goes to infinity. But as engineers who are just trying to solve this problem quickly, what do? We can just write 1 over A squared, infinity squared plus A squared to the power of 1/2 minus 1 over A squared negative infinity squared plus A squared. Yeah, thank you. Thank you. All right, so we get rho LA over 4 pi epsilon R hat. So what do we find here? Infinity squared plus A squared is going to be approximately 1. Infinity squared plus A squared is going to be about infinity, right? Assume it's going to be much larger than A. And so this ends up being 1 over 1 over infinity. Did we get that right? Zero. No, that's not supposed to happen. Oh, hold on. I missed something. I missed the numerator term. It's Z over the. Okay. Well, again, L'Hopital's rule, lazy engineer. What's infinity over infinity squared? 1 over. Okay, let's do this. Infinity over A squared times the square root of this term here, infinity squared plus A squared. It's approximately infinity squared. Take the square root of that. You have this. All right, and then on this side, so infinity over, thank you, over A squared times, same thing as here, right? So if you use L'Hopital's rule or you just use common sense here, you'll see that, as these numbers get very large, they will cancel out, and that A squared term in there will go away. And so, did I get this right? Yeah, so this ends up being 1 over A squared plus 1 over A squared. So it's 2 over A squared. So I'm just going to carry those other things down. Times 2 over A squared. And we multiply this by this here. I'll just put carrying it down here. rho L times a over a squared, so that a term goes away. 4 pi becomes 2 pi epsilon times a times r hat. Right? So the electric field, this is the final equation for the electric field. Rho L over 2 pi epsilon times a times r hat. So let's make sense of that. The electric field is always pointed in the r hat direction. There's no z component. The electric field gets larger the more charge you have. The higher your charge density, your electric field goes up. That makes sense. The rho L is on the top here. 2 pi epsilon times a. A is the distance away from that line of charge. The larger a is, the less the electric field is. This makes sense because the further you go away, the electric field should decrease, right? So this is the correct answer for the electric field here. All right, there's a lot of parts that went into this problem. All right, so it's worth a quick recap. I know that, when we start doing the math here, things start to get a little hairy. You start off with this basic relationship. Start out with the basic equation. All right, and you have to break down that equation to the different parts. Conceptually, what we're doing is we were adding up. If we want to find the electric field at this point, we were adding up all the contributions of all the charges here. One of the key points that we found was that the z component of the field goes away because of the symmetry. Every charge that's on some point on the z-axis, there's some point on the negative z-axis that is going to equal, has opposite z components, so that will cancel out. So as a result, the total electric field points in this direction. All right, so we went through and figured out the different parts of the equation. dl is equal to dz because we're integrating along the z-axis. This rho L is a constant. This AR is the unit vector pointing from some point z to the observation point. All right, and we found the magnitude of r squared here, and using Pythagorean theorem here, z and a. So we figured out AR, we figured out DL, and then the rest just becomes a math. All right. Sometimes with these types of problems, you will have to look up things on an integral table. I'll give you the integral table on your exams. Any questions on this? So I would say these are some of the most challenging problems that you'll have in this semester, because you're integrating, you're thinking about vectors, you're thinking about charge distributions, and you have to integrate on like different types of geometries. So I think these types of problems will be among the toughest, if not the toughest. So spend some time on these problems and get an intuition on how to do them. We have about 10 minutes left in class today, so what I'd like to do is to talk to you about Gauss's law and how Gauss's law can be used to solve the same problem in like 2 lines. Sure. Yep. Result. Oh, okay. Rho L over 2 pi epsilon A. A is the distance away from the wire. All right. Now, Gauss's law. I think we can just cover this in 10 minutes. What is Gauss's law? It's just a restatement of the divergence theorem. Actually, Gauss's law is the first Maxwell equation. It's del dot D is equal to rho V. Maxwell gives this to you in a differential form, but there's an integral form of it. So if I take the integral of rho V, what does that give me? So charge density in volumetric charge density, what's the units of that? Coulombs per meter cubed, exactly. What happens if you take the triple integral of that? You have total charge, exactly. Coulombs per meter cubed, you integrate that 3 times, and you get total charge. Surface charge density, you integrate twice, you get total charge. Linear charge density, integrate once, you get total charge. All right. So what we're doing here is we're from the differential form, we take the triple integral of the left side, triple integral of the right side. Bless you. And this is what you get. So the triple integral of the divergence is equal to the total charge Q. All we did here is we took the triple integral of both sides to get to the integral form number 1. Integral form number 2 is we use the divergence theorem. The divergence theorem tells us, you guys are doing problems on this right now in your homework, that the triple integral of the divergence is equal to the surface integral. Right? These are both ways to find flux, find the total flux. So the integral form of Gauss's law is telling us this. If you have charge enclosed in some volume, let's say it's just put charges in some kind of arbitrary shape like this, okay? The triple integral of the divergence, which means the total flux, is equal to the total amount of charge. So what is the total flux? It's adding up all these vectors. What was the original Gauss's law we talked about? The original Gauss's law says if you have just one charge, the field lines point away from it. This is the differential form of Gauss's law on the right. Rho v del dot v, the divergence of the electric field, is equal to the charge density. So the field diverges away from any point charges like this. The integral form of it is telling you this. If you have a bunch of charges in some volume, the total charge is equal to the total flux around that volume. Really nice. It's basically a restatement of this, except you have multiple charges in a volume instead of just a single charge in space. So these two integral forms tell you that. Okay, the total flux is equal to the volume integral of the divergence. It's also equal to the surface integral of E dot ds. And that's equal to Q over epsilon. So remember, E is equal to D, E is equal to D times epsilon. Right, so that's where this Q over epsilon came from. We just changed this D to an E. Oh yeah. Yeah. Exactly. Yeah. Yeah. Sure. Sorry for that confusion. Just bring it back to here. D is equal to epsilon E. So wherever you see D and E, they're really kind of interchangeable. You know, D is equal to epsilon times E. Exactly. Yeah. Thanks for saying that very clearly. Isaac wanted to make an important note that if D is equal to epsilon E here, epsilon is a constant, so epsilon can be pulled out of that del operator. All right, so this could also be written, this integral form could also be written del dot E is equal to Q over epsilon. Because you can pull out the epsilon and then divide by epsilon and you'll get the epsilon on the other side. But yeah, before we end class today, I really want to get to this, I want to cover this problem again. So So let's say we have an infinitely long wire again. All right, and this time we're going to actually use Gauss's law to figure out what the electric field is. So Gauss's law tells us the integral on a closed surface of E dot ds is equal to Q over epsilon. All right, what we're doing now is we're doing this problem, applying Gauss's law to the infinite wire problem. Now, to apply Gauss's law, we have to first define a Gaussian surface. And when we define the Gaussian surface, this is the key step here. Okay, this will save us a ton of math as long as you know how to do it. The key thing is you want to define a Gaussian surface where the electric field lines will be uniform everywhere. So, in other words, what kind of shape could we draw around here where all the electric field lines will be uniform everywhere on that surface? In this problem, it won't be a sphere because you have a line of charge. It'll be a cylinder. Exactly. All right, so let's draw the cylinder so everyone knows, so everyone can see this. Now, let's say we have a cylinder, and within that cylinder, we have this line of charge. Okay, now from the symmetry of the previous problem, the problem is still the same, we're just solving it a different way. If we're at some point here, what direction does the electric field point? Points away, like this. If we're here, the electric field line points like this. If we're here, the electric field line points like this. The electric field is actually the same everywhere along the surface. Do you see that? Because this is an infinitely long wire, okay? Once you start if you started to get to the edges of the wire here, then you'd start to see some changes in the electric field. But if this wire was infinitely long, every single point, if you drew a cylinder around it, every single point on that cylinder would have the same electric field. The electric field just points away from the wire. Does everyone see this? Raise your hand if you do. Yeah, question. Why do we choose a cylinder? Okay, so the charge density itself is in cylindrical, right? If you imagine a wire, so every point on the cylinder is equidistant from the center of the cylinder. Let me give you another example. If we had just a single point charge, what kind of surface could we draw on there where every point on that surface would have the same electric field? Circle sphere, exactly. Every point along this, if the charge is right in the middle of it, then you can imagine that the electric field at every point on the circle would be the same. Same thing for this problem here. If you have a line of charge, a cylinder, like every point along that cylinder will have the same electric field. If you know that symmetry and you can draw the Gaussian surface, then the math becomes super easy. All right, let's say that we know that the electric field is, we'll just call it ER. That's the field that we're looking for. We want to solve for it. So Gauss's law tells us E dot ds is equal to Q over epsilon. All right. Q is given to us. Assume that's some constant. E dot ds. Now, if the value is the same everywhere along this surface, so the surface is kind of like this. It's just the shell, okay? It's the cylinder, not the top and the bottom, just the shell. If the value ER is the same everywhere, what is E dot ds going to be equal to? This one we're actually I'm just gonna show you the shortcut here. It's gonna be ER times the surface area. Okay? It's gonna be ER, because ER is the same, because the electric field's the same everywhere on that surface. If you integrate a constant over that entire surface, you're gonna just end up multiplying that constant by the surface area. Right. I see some scratching heads. So let me just go through the math real quick, and I'll show you. Okay. So how do we do our surface integrals? Just bear with me for just another like 4 minutes here. We'll be done. Okay. ds. What is ds equal to? It has a direction and magnitude. What's the direction? We're in cylindrical coordinates, so the direction is r hat, right? And what's the magnitude? The differential area looks something like this. It's a, it's a part of that cylinder. So the direction is r hat, and what's the area? R d phi dz. R d phi dz. All right, if we zoom in here, this is dz, and this is r d phi. All right, so the area of this little wedge here is r d phi dz, and this thing points in the direction of r hat. All right, so that is what our ds vector is equal to. R hat r dr dz. Oh, that very neatly. R hat times r dr dz. Okay, now we have to dot it with. We have to dot it with the electric field. And one thing we know about the electric field is that it only has an r hat component. So we can just call that r hat er. This is an important point, right? Symmetry tells us that there's only a radial component of the electric field. There's no phi hat component. Oh yeah, absolutely, absolutely. So we see that we have dr and dz in this equation. So we obviously have to integrate from certain value of r to a certain value of z. So let's. Where did I get? Oh, sorry. Did I? R d phi dz. Yeah. Sorry about that. D phi dz. All right. You do this dot product, and you just get er r d phi dz. And what's going to be our limits of integration? Well, we have d phi and dz. So the phi is going to go from 0 to 2 pi, right? 0 to 2 pi. And z is going to be from minus infinity to infinity. Yeah. But I'm going to show you a way to do this that will make life a little bit easier. Z equals 0 to h. Okay. Let's assume that that the cylinder has some height h associated with it. This is part of the trick of Gauss's law. We're going to integrate from z equals 0 to z equals h. And this is equal to q over epsilon. We're almost done. Now, so this, we're integrating with respect to phi, and we're integrating with respect to z. There's nothing that's r dependent. There's nothing that's phi dependent here. There's nothing that's z dependent here. So we can rewrite this like this, equals 0 to 2 pi of d phi integral of z equals 0 to h of dz. And then we have the ER times R here. It's all equal to Q over epsilon. All right, this becomes 2 pi times H times ER times R is equal to Q over epsilon. And therefore, your electric field, ER, is equal to Q over 2 pi epsilon H times R. Okay. Now, there's another part here. The Q, what is the total charge in this, contained in this cylinder in terms of rho L? So this has charge density rho L, and that's given in coulombs per meter. So it's a charge density, and we want to find the total charge, because remember, this is saying Q over epsilon. Q is the total charge. Yeah, the Q is equal to rho L times H. Right, this is given in coulombs per meter, and this is meters. So coulombs per meter, you multiply it by length, you get coulombs. So we can replace this with rho L times H. This is also rho L times H. And so these H's cancel, and you're left with rho L over 2 pi epsilon times R. Right, and thanks for waiting for that. I wanted to show you that the same thing that we found here, E is equal to rho L over 2 pi epsilon A. Remember, A was the distance to the point, and it's in the R hat direction. By using Gauss's law, we found the same thing. But the radial electric field is equal to rho L over 2 pi epsilon R, and that's R is the distance. I'm sorry? So the last question, sorry everyone for taking up the time, but this is an important point. For Gauss's law, for you to be able to take this Gauss's law shortcut, you have to have some kind of symmetry in the problem, right? So you can use Gauss's law when you have cylindrical symmetry like this. You can use Gauss's law when you have spherical symmetry, right? But you can't use it in situations where there's no symmetry. So this is one of those things like you have to really think about it. If there is symmetry and you can identify what that Gaussian symmetric surface is, then you can really cut out your make your calculations a lot easier. But you have to know the Gaussian surface. So we'll do a little bit more practice with this next time. Thanks for staying a little bit extra today. Sure. Yeah, no problem. Let me just stop the recording here.